Hi, everybody. So here I am again at my son and daughter-in-law's house, helping to babysit the new baby. And I grabbed a few minutes to record a video about day 14 of Advent of Code, which is a fun one. Day 14 is all about binary math, sort of. There is this apparent computer that you are supposed to emulate, although there aren't very many instructions to it. Mostly this is just about storing data in memory. And the kind of input you get is this kind of input here, where you're given a mask, and then you are asked to store values in certain memory locations. And the mask alters the data that you're going to store. And in this case, the X's mean that the data passes through, and a 1 means that the data gets set to a 1, and the 0 means that the data gets set to a 0. And of course, this is a 36 binary bit pattern. Okay, so that's the first problem. And the goal of the first problem is just to follow the instructions that all look like this, and then in the end you take all of the cells of memory and add them all up together, and you wind up with this number here, 165. Right? That's the original goal. And the trick here is that all of the data that you are given is in decimal, except for the mask, of course. But you have to convert it to binary to do the bit manipulations and then convert it back into decimal and so on. So that's the real trick. And it's pretty easy to do. The second part of the problem, which is a little more challenging, not much more, but a little more challenging, says, well, it's not the data that's going to be masked now. It's the address. The address will be masked, and the way that the address gets masked is pretty interesting. If it's a 0, if the mask is a 0, then just copy the bit through, the address bit through. If the bit is a 1, then the address bit will be forced to a 1. But if the address bit is an X, then it will be both 1 and 0. In other words, you must use both addresses where the X is a 1 and the X is a 0. Now, if you have two X's, well, then you're going to have 4 possible addresses, aren't you? If you have 3 X's, you will have 8 possible addresses. And you must use all of those addresses to store the variable, the value in those memory cells. So in this case, we would store a 100, decimal 100, into the 4 memory cells that are defined by that particular mask. And then once again, you sum up all the memory cells and return the sum, and that's the answer to the problem. And in this second case, you should wind up with a 208 for the acceptance test. Okay, fine. Well, let me show you just exactly how that works. So the way I did this is I did it all in the test file because it's easy to do that. And so I'm just going to walk you through the tests initially. They're all down here. Let's just see if I can get to them easily. Yeah, here we are. Describe day 14, context part 1, context utilities. It should be able to turn numbers into binary strings. Okay, so, a 5 should go to a 101. Notice that I'm using strings for binary, character strings to represent the binary. I thought that would be interesting. I could have turned them into real bits, but instead I turned them into the digits 0 and 1 as strings. And of course, we should be able to turn binary strings back into numbers. So 2 decimals, string 101 is a 5. So it works. And here's the first mask test. This is for problem 1. And you can do the analysis on this if you wish, but here's the mask and here's the data, and this is what it turns into. And if you want to follow through that, you can. I'm not going to walk you through that. Next, I did a little bit of testing for the parsing. And the parsing is very simple. I want to take each of these lines and turn it into a set of commands. The commands are just lists with an identifier, an opcode, if you will, and an argument. And the mask command has one argument. The memory command has two arguments. That's pretty much it. Oh, by the way, the memory command has two arguments, both of which are decimal numbers, whereas the mask has an argument, which is a string. Okay, well, if you can do all of that, you can solve the problem. So then there's the acceptance test. This is the acceptance test from their example. And okay, I just put that in there and solved it and got the 165. So that worked. That solved part one, and the answer to part one, of course, was some horrendously large number, which doesn't really matter. Okay, now the tests for part two. And in this one, we need to, first of all, deal with this funny multiplication of the addresses, right? That those X's in the addresses will turn a single address into many addresses. So that's what this test shows. I've got this MakeAdders function that will make all the possible addresses from X annotated binary strings, okay? And you also have to apply the mask, right? The mask gets applied to the address and leaves X's in the address. So that also has to be done, and there's the test for that. And once you can do that, well, then you just do the acceptance test. Fine, great. You might complain that maybe there were some other tests that I could have written in order to kind of stair-step my way in. Well, I actually did stair-step my way in, except that I used the acceptance test as the stair-step. I did not write the full answer to it. Originally, I started by gently returning things that got closer and closer to the answer. And it's very similar to REPL-driven development. As I fleshed out the function, the return value of the function would get more and more interesting, and I would set this value to the appropriate return values, and then eventually I got the final value. So very similar to REPL-driven development, except that it was in the testing framework instead of in the REPL. And then finally, we solve part two, and that was the answer to part two. Now let's look at the code. The code is actually pretty straightforward, easy to walk through. How do you convert a decimal number to binary? You use the long to-binary string function. That's just the Java library function. And of course, the inverse of that is the long parse-long function. Again, just part of the Java library. No big surprise there. How do we mask the bits for problem one? Well, it's not too difficult, but you'll notice I'm using these reverses. And the point of these reverses, you can see here in these repeat 36 zeros. I want to make sure that I put zeros in front of the binary digits so that the two match lengths. So here you can see I've got the bit string and the mask, and I count the number of bits and I get the maximum. And then the whole point of the rest of this is to make sure that the binary number I return has the maximum number of bits of those two, and that there are zeros in the front. And in order to do that, I use this little reverse trick, because it's very easy to put the right number of zeros in the front if I reverse it and then chop it off at the end and then reverse it again. And I'll let you work through that. This for loop is where we actually do the masking. And it should be kind of obvious. If it's a 0, make it a 0. If it's a 1, make it 1. And if it's an X, just copy it through, right? Pretty straightforward. How do you parse the line into a command? Well, that's just a bunch of string start withs and some ugly regular expressions. And I'll let you work that one through. It's not very difficult. And then here's the solve. This is the first solver. Very straightforward. I split the lines. I map them into a bunch of commands. And then I go into a loop. The loop starts with a mask of nil. We presume that the very first instruction is a mask instruction. That seems to be the case. We start with memory as an empty hash map. Okay. And then we have the commands. And this is just a destructured way to get the head and the tail of the commands. All right, and then, okay, if the command is nil, well, we're done. So just add up all the values in memory. If the command is a mask command, well, then recur with the mask as the argument and the memory and the tail of the commands. And if it's a memory command, well, then, get the value as the third, right, 0, 1, 2, third element of the command. Get the address as the second element of the command, and then the result is the decimal value of masking the bits with the mask and the binary of the value. So it works just fine. And then you recur with the mask and you add to the memory and the tail of the commands. Very straightforward, works fine. Okay, next. MakeAdder. This is for part 2. And for part 2, I'm going to come down here first to MakeAdders. Given an address with X's in it, I want a list of all the possible addresses that it could be. And that's what this code does here. And it's not very difficult, right? I just get first of all, I get the number of X's in the address. So this is the number of X's. And if that's 0, I just return the address. If there's no X's, return the address. Otherwise, okay, we start with MathPow2, right? We're going to find out how many addresses we're going to create. And that's, of course, 2 to the XS. And we get the integers 0 from up to that number. And I turn those into binary strings. So patterns now is all the binary strings of the X's. And then there's just a little bit of making sure that there is 0 padded and so forth. And that's what these 2 next lines do. Make sure that they're as long as they need to be and there's zeros on the front and so on. And then we just loop through the pattern, one bit at a time, one address at a time, one address at a time, all the patterns, right? And if the pattern is nil, we're done. So we just return the results, which will be the list of addresses. Otherwise, we recur through the tail of the patterns and we conj the make address into the results. So this MakeAdder function is the thing that actually masks them together. So let's take a look at MakeAdder. MakeAdder takes a pattern, one of the patterns of the address, and it takes the address itself, which still has the X's in it, and then it loops through the pattern one bit at a time, and it looks at the address if the address has got an X, or the pattern if the pattern's got an X in it. If the address has got an X in it, this is the masked address. If it's got an X in it, well, then we're going to recur with the rest of the patterns and the rest of the bits, but we're going to move the pattern bit in, right? So if there's an X, we move the pattern bit in and we adjust the pattern and we adjust the bits, and otherwise we recur with the original pattern because we haven't found an X, right? And the rest of the bits and so on. And if there are no more bits left, then we apply stir to the address, which takes all the characters and jams them together into a single string. Okay, and then how do you mask the address? Well, that's just as simple as the other one was. It's got the same reverse thing here, except in this case I use subvec instead of substring, but same idea. And then the same idea for the for loop, except that it does it a little differently, but I'll let you deal with that. And then eventually we need to solve. Now how do we solve it? Well, we loop through the commands, right? And for each command, if there are no commands, then we do this reduce plus vals again, just sum it all up. If it's a mask command, same as before, we just set the mask and continue. If it's a mem command, well then we have some interesting work to do. So we first of all, we get the address, which is the 2 binary of the second argument. And we get the value, which is the third argument. And then we loop, we recur with the mask and the store vals. This function will return the new memory cells after they've all been stored using the mask, the address, the value, and the existing memory. And we do that with the rest of the commands. And that's where store vals comes in. So store vals now we know we've got a mem command and we've got to store a value into an address according to a mask. And so we mask the address and then we make the addresses from the masked address. That's the adders. We loop around that. If we're out of addresses, then we return the memory. Otherwise, we loop through the rest of the addresses and associate the 2 decimal address value and blah, blah, blah. And that's it. That's all there is to it, guys. That's the whole thing. So I just thought you'd be interested in seeing that. I didn't show it to you in process because I really can't take an hour or more with the granddaughters and the dogs and everything else going around here. So just a quickie. Hope you enjoyed it. Have fun. Enjoy the holiday season. All that stuff. Bye-bye.